Now I want to look at a correlation, which is actually the word is used a lot in different contexts to mean a general association. You'll hear people talk about, oh, there's this correlation between two variables. But we're being very careful in this class to say, oh, there's an association between two variables, because actually correlation is a specific numeric measure of the association between two variables that have a linear relationship. Okay, and this is very important. We'll see why nonlinear relationships can mess up correlation. So correlation assumes that we've already checked that the two variables are linearly associated, that is, have a linear form. And then we can compute this correlation, which communicates very quickly, rapidly, the strength and direction. So the other two factors, the strength and direction of the association. The way this is encoded in the correlation is the sign. You can have negative correlations, you can have positive correlations. Those show the direction of the association. So that is a negative correlation goes with a negative association, and a positive correlation goes with a positive correlation. The direction, sorry, the strength of the association is measured by the magnitude. So anything close to zero, any of the correlation values that are close to zero, means there is a very weak association. And the farther I get away from zero, the stronger I have in terms of my association. Okay. What's interesting is that the correlation, the way it's computed, we won't get into the details, but it turns out that you can show that it always has to be between -1 and +1, this number. So when I'm far away from zero, I actually mean I'm either close to -1 or close to +1. So it has this notion that those are strong correlations. Here are actually a bunch of examples. So that the graphs, the scatter plots, are scatter plots, and above each one is the amount of correlation in that scatter plot, with I should say the correlation that's computed from that scatter plot. So you notice that when I have a 0.9 correlation right here in the top left, okay, that's what that R equals 0.9. But R is the universal symbol for correlation. I'll talk about that in a minute. So you notice that I have this linear relationship. In fact, all of these graphs have a linear relationship. You might not be able to see it in some, but this one's pretty clear. It has a linear relationship, very straight there. And yeah, those points stick very, very close to that line. So I have a very large in magnitude correlation. 0.9 is pretty close to 1. It's far from 0. So I have a strong correlation, and 0.9 is a positive number. So this is going to be this shows that this is a positive association. Oops, sorry about that. So that association, that correlation shows that those two aspects, the strength and the direction. And so in fact, along this top row, all of the correlations are positive, all the associations are positive, but you notice they get weaker and weaker. So a correlation of 0.7 you can still see the line there, but you've got quite a bit of scatter around that line. And 0.5, it looks maybe a little bit more scatter than the 0.7, and that's the funny thing about the correlation, is it sort of gets worse very quickly, but then kind of levels off in terms of the amount of scatter. So that's that 0.5 is a little bit more scattered. Then you get down to 0.3 here. You start. Is there a line there? Does that line go? And the answer is yes. There actually is. I mean, I've set this data up so that it follows a linear form, but you can start to see that it gets kind of blurry because there's so much scatter around the line. And so that's why that correlation, it's 0.3, it's getting very, very close to 0. And then just would go crazy, you go 0.1, and now it's even hard to see that there's a line. This is just a big cloud of points. Basically, so close to zero that most people would say there's no association. Okay, even though the correlation comes out to be something like 0.1, that's really so close to zero that we might as well call it zero as far as correlation is concerned. In the second line, I actually have 5 other graphs, and notice all of them are negative. Both the correlation and pretty clearly the association we see in the scatter plots. The form of that association is negative. They're all linear again, and we can see the strength, right? So we start over here at negative 0.2, and yeah, maybe you could see there's a line there, but it's not very clear because there's not much association. Then negative 0.4, a little less scatter. Negative 0.6, a little less. Negative 0.8, yeah, you're starting to see congeal around the lines. And then negative 1. And here's an interesting fact. You can only get negative 1 if the points lie exactly on the line. Okay, there's no scatter at all. Positive 1 is the same way, but just obviously in the other direction. All the points lie along a line. And I did this sort of to see a contrast of 0.7 to 0.8 here, because really, even though this is positive 0.7 and this is negative 0.8, really the magnitude is 0.7 and the magnitude is 0.8. Those show the association. The negative or not is just telling me which direction. So a positive correlation of 0.7 will look a lot like the correlation of negative 0.7, but just in terms of the scatter, it's just will be in a different direction. So that sign serves that point. Okay. So now let's look at some of the data sets that we had examined before. This is the women's clothes and the food costs, and I went and computed what the correlation was, and it came out to be 0.774. So that's pretty good. That's not terrible. It's not that close to zero, and it is positive. And you can look at the scatter plot, and remember we did actually devaluate the scatter plot, that it was linear form, a positive direction, and moderately strong. Okay, and so that the correlation is telling me the same story. But does not hurt to remind you that actually one of the things the correlation doesn't tell you is the form. And in fact, I need to make sure that the form is linear before I do any computations. So plotting it is going to be really important. Here is the vacation days and food costs. And what we had seen before is that there's really no association here. It's a big cloud of points. And sure enough, when I compute the correlation, I get a negative 0.022. That is darn close to zero, right? I mean, it's 0.02. So that's very close to zero. Yes, there's a negative sign. So this, in some sense, is saying that there's a hidden, line that goes down from left to right a little bit of those points. But you really can't see it because things are so scattered. This is the magnitude of the correlation being close to zero actually turns out to make it not very dependent on the direction. So a positive 0.022 and a negative 0.022 are very hard to distinguish. They look basically, because they're both close to zero. How do I compute the correlation? And I'm just going to work through the details slightly, lightly, because it's not that important, but actually knowing it a little bit will help explain some things that come up later. So here is a data set of heights and weights of a bunch of individuals. I'm assuming that they're the same gender. Just makes things easier because otherwise we get bimodal things and so forth and so on. And so yeah, I think that it's definitely one gender. And over to the right, you see I say green positive, red's negative, and blue's no association. Well, those colors, that color code, will come into effect in a second here. All right, so how do I compute the correlation? Well, the first thing we do is we compute the means of each of the variables by themselves. That is, I compute the mean height. And I think I've mentioned this before. You can imagine taking all of these points and sort of pushing them down onto the x-axis to do a histogram, per se, for example. And I can also just sort of take the list of heights and take their average, take their mean, and sure enough, that I get some number. Okay, somewhere I think it's at 66.8 or something like that. The data set, I don't remember exactly what the numbers are, but something like that. And so the mean height has been computed. And then I do the same thing with the weight. So think about taking all these points and pushing them to the left at the weight. That's going to give me a distribution and a direction of the stream and all of that. So, but I can compute the mean for that as well. And find out that it's actually a little less than 150. All right, and so once again, you got these arrows pointing at the axes. What we want to do is sort of coordinate those two, right? Go sort of up from the mean height and over from the mean weight, and where they intersect, we could consider that a very special point because it's the means of both variables. Okay. But notice what it does is it divides the points into 4 quadrants. Those 2 lines. Imagine this being these 4 quadrants. These points, those points, those points, and those points. And what I should do in thinking about these is I should sort of indicate which ones help bring my correlation up, that is closer to +1, and which ones bring it closer to -1. Okay, back down, and so we could color code them, and notice that what I've done here is I've taken these points in the upper right and lower left corners, okay, and colored them green because in some ways those conform to a positive correlation. If I look on the other hand with the red points, so over here and down here, I can say that those are negative. They sort of contribute to the correlation in a negative way because in some sense they want to make the line go negative. Okay, the blue ones are on the fence, right? They are exactly equal to the mean for one of the 2 variables, and it's usual to say, well, those don't really count. Okay, they have no association because they don't fall into any of the 4 quadrants, and so it's not possible to say how they affect the relationship of these 2 variables. So now what? I want to just talk about the fact how I use that idea. I want to add up the greens and the reds and the blues. The blues won't contribute anything, but I add up the greens and the reds and sort of say, well, who's going to win this battle? It looks like there are a lot more greens than there are reds, so it does look like the greens will win because there's more of them. Okay, so how do I do this in for real? That is with pencil and paper. The answer is the first thing we do is look at the z-scores. Now we have not covered z-scores in the class yet, but the idea is simple enough that a z-score will be a positive number for a particular point. Okay, will be a positive number. So let's say right here, this point right here will be positive if it is above average in a particular attribute. Okay, so this point red is positive in terms of the height because that one person, that one red dot represents a person, was taller than average. Okay, where the green dots, on the other hand, okay, are people who are smaller in height than you would expect. Okay, so these green dots are smaller than the height of the average height. Sorry, they're smaller than the average height. So I can now notice that all was about the height. Now I can look at the weight. Okay, the weights and are for these dots down here, not all of them, but right here, are green dots that are below average in weight. Notice they are like at 100 pounds, 125 pounds, and the average weight is somewhere up at 148 or so, 140. where these red dots up here are actually above average in weight. All right. So now we have these 4 quadrants, and we can actually talk about the 4 set kinds of points there. These points here are people who are above average in weight and above average in height. So they're above average in weight because they're over that 150 limit, and they're above average in height because they're over that, what is that, 66-inch average. Okay, so they're both above average. The bottom below that is right here. These points right here are below average in weight and above average in height. Okay, right, so that's kind of surprising. That doesn't fit the norm. Here are a bunch of people in this quadrant that are below average weight and below average in height. Okay, so their height and weight go together. And then finally, this 4th quadrant right here has those individuals that are above average in weight but below average in height. Okay, so everybody in these 2 quadrants, 1 and 3, these 2 right here, in some ways go along with the pattern, the general pattern, more weight and more height. Where the ones in red, the other 2 quadrants, are the points that don't go along with that consideration. So how do I combine all this? Well, the correlation, we're going to use these z-scores because remember what I said a little bit just a minute ago, that z-scores are positive if you're above average in a particular variable and negative if you're below average. So when I get z-scores that are the same right here, like these up here, because why? Well, because it's above average in each of the variables, and the z-score is going to both be positive. Those are going to have a positive product. So that's what down here, I'm multiplying zx times zy. So I take each one of these points and I say, what's your z-score? I say, oh, it's a positive z-score in height, a positive z-score in weight, and so my 2 z-scores are positive, so their product will be positive. 2 positive numbers are positive. Here's the interesting one right down here, these points, because what happens is that they are below average in weight and below average in height. And so I might, ask somebody to compute, what does that mean? Oh, you get 2 negative z-scores. Okay, great. But they do go along with the pattern. And in fact, in my computation, what I'm going to take is those 2 negative z-scores, multiply them, and this is where it's interesting, is mathematicians will tell you, well, a negative times a negative is actually a positive. Okay? So indeed, when I take the 2 z-scores of the green dot,